Can I?
Yeah. So, dear friends and respected senior members of INS, I once again welcome you all to this INS webinar program. And organizing webinar talks by eminent speakers and the prominent persons who have made significant contribution in the field of nuclear science and engineering and technology is one of the important activities of INS. The aim is to bring to the knowledge of the members the newer development and achievements in the department and in the area of science. Today's talk, that is the 28th webinar, will be given by Shri Biplob, former Facility Director, BARC Facility, Kalpakkam. He is going to speak to us on nuclear waste management in India, strategies and processes. So he is stationed at Kalpakkam since 1983 when he joined DAE, and he has seen the growth of waste management strategies very closely and has made significant contributions since then. If you remember, our 9th webinar was given by Dr. C.P. Kaushik on the advancement in the back-end and nuclear fuel cycle, Indian perspective, on 13th November 2021. Now we hear on the waste management strategies. Friends, as we all know, the prime objective of the waste management is protection of public, environment, and future generations. Each of these topics, each of these objectives speaks volumes of work and achievements made by DAE. Safe management of the waste has been accorded highest priority right from the inception of nuclear program. In this pursuit, we have successfully extracted wealth from the waste. DAE has achieved complete indigenization of this technology and reprocessing of spent fuel from PSWR. As we follow closed fuel cycle, the strategy has been to implement optimum utilization of fuel, less amount of high-level active waste, and reduction in the long-term isolation. The second stage of the department is entirely dependent on the success and performance of the waste management. Shri Paul is going to talk more on these topics. On behalf of INS and on behalf of the INS webinar committee, I welcome you, sir, to this webinar program. So before we call him to give his talk, Dr. Manchanda to introduce the speaker to our viewers. Manchanda ji?
Yeah, it's my turn. Okay.
Yeah.
So friends, my name is Manchanda. It is my privilege to introduce the honorable speaker for today, Shri Biplob Paul. Shri Paul graduated in chemical engineering from NIT Durgapur in 1982 and joined centralized waste management facility Kalpakkam after graduating from 26th batch of training school in 1983. During the initial years, he worked in the field of air cleaning engineering, which included testing and certification of HEPA filter and iodine filter installations of various nuclear facilities at Kalpakkam. Later, he served as superintendent operation and then as plant superintendent of the centralized waste management facility, which manages all radioactive solid waste and low and intermediate level liquid waste generated from various nuclear facilities at Kalpakkam site. He has played an important role in the development of a first of its kind melt densification system for volume reduction of contaminated plastic waste. Under his leadership, a process was also developed for treatment of technetium containing radioactive liquid waste. The latest addition for volume reduction of solid waste was the 200-ton compactor for solid waste drums as well as HEPA filters. In 2019, He became the general manager of the integrated nuclear recycle plant of NRB at Kalpakkam, and later took up the responsibility of the director for BRC facilities Kalpakkam. During his tenure, two important facilities, uranium oxide facility and vitrified waste storage facilities, were commissioned at Kalpakkam. He superannuated on 31st March 2021, and his group has received many awards, and also the facility which he has created, it was deeply appreciated by several awards from the department. With these words, now I will revert back to the speaker.
Thank you, sir. Thank you very much for introducing the speaker. I'll now request our president, S.K. Mehta, to give his opening remarks.
Let me welcome you, Dr. Paul. From the biodata I have heard, there is a lot to hear from you and learn. One of the criticisms that we face from public is the waste management arising out of the nuclear power program. I'm sure today we will learn much more to answer the question they raise. So let me welcome you, and I look forward to the talk from you and the discussion that will follow. Welcome. Thank you again.
Now, may I request Shri Paul to begin his presentation, please?
At the outset, let me thank INS, Dr. Mehta, Dr. Ramarao, and the committee, organizing committee, for giving me this opportunity to present this lecture on waste management. Okay, though I have named it as nuclear waste management in India, let me share that my experiences have been mainly in Kalpakkam. So I may make some passing references to the other sites like BRC and Tarapur, but mainly I will be talking about the facilities at Kalpakkam, where I have grown actually in DAE. So slide has changed, no?
Yeah.
Okay, so all of us always start with this particular slide. One more remark I would like to make here. I am assuming that there are people who are not exactly from DAE, or they are not from waste management side, and they are not that familiar with waste management. So I will touch upon the basics in the first part of my lecture. So starting right from the Indian nuclear fuel cycle, the main difference between the nuclear fuel cycle of India and those followed in other countries, in many other countries, is that ours is a closed fuel cycle. We don't stop at power production. We reprocess the spent fuel and reuse the products back, thereby reducing the quantity of waste generated. So I cannot use a pointer here, but I'll just try to bring out. So this slide is known to most of us. I'm just for the people who are not from DAE or who are not familiar, I'll just repeat once that uranium is mined and made into fuel in oxide form, and then it is fed into the power reactors where it generates power. The spent fuel is transported to the reprocessing plant, where after some storage, the fuel is reprocessed. The reprocessed fuel produces, we get back useful materials like uranium and plutonium, and we get different types of categories of waste, which we'll be elaborating later. and thus we try to reduce the total volume of waste generated in our Indian nuclear fuel cycle, and also get back the useful components like uranium and plutonium. This is another slide showing the same information. So I will go ahead. Only thing here, additional part is that the high-level waste which is produced contains fission products, actinides, and that comes for treatment to WIP. And of the fuel, only 1% fuel gets converted to fission product. So the entire part of uranium and small quantity of plutonium produced can be reused. And Dr. Bhabha envisaged a three-stage nuclear power program in which we start with uranium as the main fuel, and the stage one, they are the pressurized heavy water reactors, and NPC has done very well. It has 22 operating reactors, and it has targeted to make 43 reactors operational by 2031. So the first stage of our program is quite successful. And here I would also like to say that from the initial 220 watt megawatt reactors of MAPS and Tarapur, we have scaled up to 500 megawatt and then to 700 megawatt. And gestation period for construction of the plants have been reduced. And this the power is expected to reach 22,000 megawatt by 2031. So there are LWRs also, that is light water reactors, also operating in our country. 2 in Tarapur, which are quite old, and 2 VVERs operating in Kudankulam. Now coming to the stage 2, the fast breeder reactors. These take plutonium with uranium as input and produce more fuel than it consumes. So this stage also we have come good way. The FBTR was commissioned in 1984-85, and it has been working quite well. And the 500 megawatt PFBR is under commissioning, and we hope to soon get it operationalized. It has got a huge power potential because we are able to reuse the fuel which we generate. And since we have a limited stock of uranium in India, and we have got a huge store of thorium, the third stage is automatically thorium-based reactors, of which a 30 kilowatt reactor is operational in Kalpakkam again, the Kamini, and 300 megawatt HWR is under development. So here, as I told, that because of the huge stock of thorium available, we have got a large potential, but there are several challenges to meet, particularly in reprocessing of the fuel. Now, as Mehtaji was pointing out, nuclear waste management becomes important because of the public perception of nuclear waste as something dangerous. So we have to always meet our limits, the discharge limits, and show to the public at large that we are well within limits and everything is running safe. The public as well as the operating people, both are safe. The reactors are safe. The plants are safe. So then waste management plays an important role in meeting this requirement. And closing the fuel cycle is a safer option, and waste is better managed. So they are also, but only thing is we are having more variety of waste coming in, which we know how to do. We have got very good experience on managing the various types of waste which are additionally produced due to reprocessing, and I will go to that also. And of course, the minimum burden to the future generations. See, the reactors which simply operate and store the spent fuel, they live the next generation with an uncertainty what will happen to the fuel till they have some solution for it. But we are not leaving it to the next generation. We are taking up reprocessing right away and then taking care of the waste also. Now a little bit about the reprocessing of spent fuel. Spent fuel is chopped and then dissolved in the dissolver, and the feed solution is taken, and using the Purex process, it is by separate extraction cycles, we take out uranium and plutonium, and several decontamination cycles are there which take out the which concentrate the high level waste and also produce some of the intermediate level waste in alkaline form. So this slide shows a little bit more on the waste side. I have not talked about the hulls. Yes, the hulls are produced during chopping, and these right now are going to the low-level waste management plants for storing in tile holes. So these are also alpha active and would need long-term management for it. As I said, the first cycle raffinate becomes the high-level waste, and in the various cycles, we also get some LLW as well as ILW. Maximum quantity is LLW, smaller quantities HLW is maybe around 500 liters and about 5,000 liters of ILW per ton of fuel processed. Now I will go to the basics. Please, I will request my seniors to pardon me for going into these basics. I'm assuming that there are some listeners who would not be knowing about this, so I'm just going through these slides. Nuclear waste, how it is different from the conventional waste is that it can, the external exposure, that if you are near the nuclear material, you get dose from it which can affect you. And if depending on the amount of dose taken by the body, genetic effects could be there. Similarly, and the third point is that the waste persists in the environment based on its half-life. If a longer half-life material is produced and it is going to the environment, it can be lingering in the environment for many years, thousands or millions of years also. So these become the points of concern for the layman, and we have to clear all these doubts. How we manage to take care of the waste so that only the exempt waste, that is the waste which is equivalent to or less than the uranium present in the environment, only that grade waste is disposed based on the limits set by the authorities. So our waste management objectives are very clear. Protection of human health, environment, and protection of the future generation. Based on the previous slide, I think I need not explain further. So now the objectives of waste management are achieved by minimization of the waste generated, treatment of waste before discharge, and immobilization of the activity which has been taken away from after decontamination in a safe place. The decontaminated liquid or gases are only allowed to go out into the environment which are at exempt level. So it should be made very clear that we don't allow any radioactivity which is of higher concentrations to go out. We take care at our plant level to decontaminate these wastes and release only the decontaminated liquid or gases. Three basic tenets are followed in rad waste management. First one is delay and decay. The isotopes which are of short half-life, particularly beta gamma activity, are being reduced in this way. That is holding the radioactivity sufficiently so that it comes down, the total activity comes down and it can do less damage. This delay and decay principle is also followed in many normal operational requirements as normal requirement, where we know that, say, whatever spent fuel comes out of a reactor is not immediately taken up for reprocessing. We hold it, it decays. Many of the short half-life isotopes decay down, and then we take it up for processing, which becomes easier to reprocess also. Concentrate and contain. This is the principle followed for the isotopes which are large in concentration and which have higher half-life and which need to be stored for some duration. The third one, dilute and disperse. There are certain streams coming out from various radiochemical plants which have very low activity. So it's possible to monitor them. Once we monitor and find that they can be diluted, and dilution is permitted, say up to 20 times dilution is permitted, and we dilute it and disperse it into the environment so that they are no more harmful to the environment. So this recycle and reuse we have written here, but this is that finally our principle would be that maximum quantity of material which we call as waste is taken back into the plant and reused in some way or other. And it's true that as the technology develops, we are finding uses for the various isotopes, various components, various streams, and we are able to take back the radioactivity and recycle back either in the plant or produce something useful from it. The various isotopes have already shown very good promise. We'll come to that later. This categorization of radioactive waste, this table, I would like to just discuss one or 2 points here. One is that the liquid and gaseous waste, they are categorized based on the amount of activity present. That is the concentration of the radioactivity in the liquid or in the gas. In case of solid, since the radioactivity could be dispersed in various non uniform way, so the radioactive packages, solid waste packages are based. The category is based on the surface dose of the package. Of course, excepting the alpha bearing waste which contains alpha and which is known to contain alpha based on the source, anything which has more than 4,000 becquerel per gram of alpha is marked as alpha waste, and this cannot be permanently disposed in any near surface disposal facility. This has to be taken up for further treatment. Now, very generally, if we speak, waste management plants, they follow a strategy of taking up a stream, say a liquid waste stream or a gaseous waste stream. Take it, the stream, we separate it out into two components after treatment. One is a concentrate and other is a decontaminated waste. So the concentrate is can go back to the plant for further treatment, and the decontaminated waste, if it is sufficiently having sufficiently low activity, can be discharged into the environment. So what happens is generally the volume of the decontaminated waste would be large and the volume of concentrate would be small, so that we can take it up for treatment or conditioning and disposal. Now, waste management process starts right from the generating plant. One important step here is segregation. And probably before segregation is one more step, that is minimizing the amount of waste, which is imposed by the regulatory authorities so that the plant follows proper discipline to generate minimum quantity of waste. And the segregation is done so that later when they come for treatment, the waste can be treated based on the different types or treatability of the waste. This will become more evident when we come to solid waste management. In the same way, liquid waste also can be planned to, while designing the plant, it can be planned so that the streams are segregated in such a manner that the following uh, treatments can be taken up easily. So we need a very close coordination between the waste management and the waste generating plants. And here the regulatory authorities come into picture. They impose restrictions so that there is a early interaction during design between the designers of the plant as well as and the waste managers. So gradually this has been very well implemented in DIE, and due to which the waste managers are able to much better way manage the waste. So if we look at the full gamut of waste management, we can classify the waste as either solid, liquid, and gaseous, or again within them low level, intermediate level, high level, particularly for liquid waste. And treatment, of course, is for each one there are various treatments. Like liquid waste, a major part of the volume, large volume of liquid waste is treated with chemical treatment, ion exchange, reverse osmosis, and evaporation is used for smaller quantities for higher concentration waste. Solid waste can be compacted, incinerated, and there are several other procedures. So we'll come back to that again. Gaseous wastes, of course, are basically produced, are handled at the site, at the plant itself, and it will not come to the waste management agencies generally. So these are basically filtered. Adsorption is also used for gaseous components. Pre-filtration and HEPA, high efficiency particulate air filters, are used for final filtration of the particulates. There are several conditioning techniques. Actually, I have not touched upon conditioning. Conditioning is a technique by which we make the different treated waste or the concentrates which we get from the various treatments to make them into a form which is acceptable for disposal. So various conditioning techniques are there, like cement fixation, polymerization, bituminization, and of course vitrification. So if you see now the popular ones which have stayed is cementation and vitrification. After the waste is conditioned, it is stored in the solid waste. That is, interim storage is done for alpha waste, because as I said, alpha waste cannot be disposed into the near surface disposals, and they are they may be further treated also. And vitrified waste also has to be stored before it goes to the final disposal in air cooled storages. Disposal, again coming to disposal, various kinds of solid waste disposal facilities are created with proper engineering. We will go into detail of that. I think right now I will skip this part, and same way for HLW also will come into the treatment and storage later. And of course, environmental monitoring is an important function which is connected with waste management. The environment, once we dispose a liquid waste into the environment, like we dispose into the sea, it's required to check if the disposed liquid activity, what is the final activity at various distances. So there are special agencies, particularly it is done by the ESLs, Environmental Survey Labs. Similarly, they also take samples from the near surface disposal facilities of the like of CWM. It has got its own NSDF. So around the NSDF, there are boreholes from which samples are taken, soil samples are taken to check if any activity is moving out of the NSDF. Now, so solid waste management, it is in case of solid waste management, we basically try to reduce the volume of the waste, because it is already, it has been, solid waste is generated mostly after treatment. So we try to reduce the volume or conditioning it. So the solid waste which comes from the various plants, like plastics or uh, used materials which are contaminated with radioactivity, these can be further treated. We'll go into detail of that, like compaction, belt densification, incineration. All these techniques are available for treatment of the solid waste. And processed solid waste are disposed in near surface disposal facility. Generally, these NSDFs are co-located with nuclear installations to avoid transportation of radioactive material and for better institutional control of the NSDF. Since we plan to do this monitoring for next 300 years to see that the waste comes down to the exempt level. Liquid and gaseous waste, generally, like I told earlier, we minimize the activity which goes to the environment and get a concentrated quantity of slurry from there. So the bulk of the liquid goes out, and small quantity of slurry or sludge is obtained, which goes for treatment. So discharge of treated waste into environment is in line with the principle of LRI, that is as low as reasonably achievable. And secondary waste conditioned, it is conditioned and disposed in NSDF. In case of high level waste, so there we separate the major fission products, and already in BARC, we have already demonstrated that cesium pencils have been made and they have been utilized, and several, and then also other applications have been shown. So HLW volume is reduced and it's conditioned in glass, and it is interim storage is done at VW, that is vitrified waste storage facility, and the final disposal is in deep geological repository. As I was telling, that several useful or variable materials can be obtained. Cesium-137 is already in use. Strontium-90 also has been demonstrated for use in power packs. Americium-241 is also useful, and then palladium, rhodium. These are noble elements which have wide industrial application. So these are some of the wealth which we get from waste, and every day newer opportunities are being opened up. Now I'll come to the centralized waste management facility, where LLW treatment and solid waste management are the main activities. There are other activities also. I would like to share with all of you that this facility came up quite some time back. Shri R.V. Amalraj, with his small team of engineers, came in way back in 70s, and construction was started. The plant was commissioned in 83-84. Later, Sri Jalil Ahmed took over as the head CWMF, and construction and commissioning of more systems were continued. And before CARP was commissioned in 1997, 98, and later Sri Kevilal was the plant superintendent. And in 2006, Dr. P.K. Sinha became the plant superintendent. So during these periods between after 1984, MAPS was operational and FBTR also was operational, and several other labs of IGCAR were producing waste, and these were being treated. After 1987-88, by 97-98, CWMF was ready for taking waste from CARP, and higher active waste started coming. And Dr. P.M. Satyasai was the operations superintendent at that time. And later in 2006, of course, after Dr. P.K. Sinha came, I also joined him as the operations superintendent, and we started receiving some more waste. So here I would like to recall all my seniors and thank them for bringing up the plant, and I have learned so much from them. So I will go to this slide now. These power reactors, you know, the MAPS 1 and 2 are there, which and fast breeder reactor at Kalpakkam, and several nuclear research facilities of IGCAR, reprocessing plants, RDL, that was the FBTR fuel pins are being reprocessed in RDL. CARP and P3A, of course, is our own NRB's part, and FRFCF is coming up. It's a very big plant which is coming up at Kalpakkam. And then waste, after WIP became functional, we started getting another set of wastes which were again challenging. So gradually we have been facing the challenges and taking up the various streams, finding out treatment methodologies and treating the streams at CWMF. But as Dr. Sinha had always been saying the mainstay has been chemical treatment. Huge volumes of waste have been treated at CWF through chemical treatment. We'll go into detail of that later. PFBR is also being commissioned, and it has got its own set of liquid waste, some of which will be coming to CWMF, and part of its plant has been made within PFBR premises, which will be operated by again CWMF people. And of course, we get disused sources from the non-DA installations of South India, which are disposed at CWMF. This slide shows in short the liquid waste management plant. The pre-treatment tanks receive the waste, and the next picture is of the clariflocculator where the treatment is carried out. Here, this does not show a very important part of the treatment process, that is the dosing chemicals, addition of dosing chemicals. I will come a little after a few more slides on that. Then after that, the supernatant from the clariflocculator is collected in the post-treatment tanks and discharged to sea after monitoring and dilution. The discharge point for Kalpakkam is MAPS jetty, and we have now planned to shift the discharge point from MAPS jetty to PFBR jetty, where dilution pumps have been separately installed for taking care of the larger quantities of waste which are expected after all the plants are operational. The concentrate from the chemical treatment is centrifuged in a decanter centrifuge, and the slurry is fixed in cement, after which it's collected in drums and disposed in RCC trenches in the NSDF. So these are a few more pictures of the chemical treatment plant. The typical for cesium and strontium, copper ferrocyanide and calcium phosphate is used for precipitation. They are co-precipitated with these at some pH of 9.5. Here, what I was telling that what we found with our experience is that the addition of chemicals, which has to be done as the liquid is pumped into the clariflocculator through a flash mixture, all the chemicals need to be added in the proper dosing percentages, and so we need separate dosing pumps. So there are some 7 tanks from which the chemicals are fed using separate dosing pumps and in which each one's rate is fixed, so that throughout the treatment of say 150 meter cube of liquid we are treating at a time, throughout this feeding of and when they go and mix in the flash mixer, always the ratio of each chemical is maintained, and this has resulted in very good DF in the clariflocculator. And we have got the confidence. Initially, we faced problems like one treatment would show a good DF and the next treatment would not be giving the same DF. Of course, there is one more important step before this, which our lab carries out, that each time a tank full of slurry, a tank full of waste is ready for treatment, we have to characterize it and do jar tests in the lab to see that the dosings which we have planned are correct or not. And every time the lab tweaks the dosings to see to modify to get the best DF possible with the particular tank of effluent. So here Now, Sri Shanmugamani is the chemist who is doing this, and with him Advitya. They are right now there. There have been several people before them, Chitra, and I think Shanmugamani has been uh, groomed by none other than Dr. P.K. Sinha, who is an expert of liquid waste treatment by chemical treatment. And so this I wanted to emphasize that it's very important to feed the chemicals in proper proportion throughout the treatment phase. Otherwise, we'll never get the required DF. And this has been the lifeline for us because large quantities of waste have not only come during car modification time when there were small leakages and all that, which had to be treated. Even after that, WIP became operational and more waste is coming, which is regularly needing treatment. So it has been a boon for us that the entire process has been standardized and is working very well. Sri Khandelwal is the operation superintendent. Sri Anji Reddy is there. These two engineers are the lifeline, and they are looking after the CWF plant right now. Now I'll come to this technetium treatment. We had faced a problem after WIP started operating. We found that a particular stream of waste which comes from ILW treatment, that is it's category 4, and it had very large quantities of technetium. It also has alpha. So due to this technetium, we found that the usual treatment would not remove technetium. So actually there were so many tests done and so much of after the trials, the this particular dosings have been fixed up, and like what I'm showing on the screen, sulfite, which is an oxygen scavenger, then ferrous reducing agent. It reduces technetium from technetium 7 to technetium 4. And of course, copper ferrocyanide is present for removing the cesium-137. Ferric is present for as a flocculating agent. And pH has to be controlled very precisely between 8 and 8.5. So if ruthenium 106 is present, copper is goes to 80 ppm of copper is also required to be added. So here I will say that because the technetium is precipitated as technate, pertechnate, it's insoluble, and we have to understand that because of its insoluble nature, once it is fixed in cement, it remains in that condition, and the leaching studies have shown that it is the leach rates come down gradually, and within and it matches the leach rate of any other cement fixed waste drum. CWF has a decontamination center which is doing a regular work of decontamination of protective wears like coveralls, lab coats, gloves, shoes, face masks, and respirators. So it has got several equipment, industrial washing machines, hydro extractors, dryers, etc. I would like to specially mention this respirator decontamination. Uh, During modification of carp, huge number of respirators were being used because there were several cell entries every day, and they were coming out in thousands. And before at that time, Dr. Satyasai, who was the operations superintendent, he took it up as a challenge and he developed a procedure and got it approved by the safety committees. And not only that, then decontaminating large number of respirators was a huge challenge, because you have to remove the last particle of alpha from it, because they are being used on the face, directly on the mouth. So, and CWF could meet at that time the challenge, and the operation staff were motivated by Dr. Sai, and they could really perform and decontaminate thousands of respirators, saving lakhs of rupees, and also saving a lot of disposal space in our NSDF. Now, this slide is for completion's sake. Gaseous waste, as I mentioned earlier, the gaseous waste, which also contain particulates, the ventilation streams, and various other streams. In the nuclear reactor operation, for example, iodine-131, tritium, and argon, argon is particularly produced in MAPS because of air cooling of the coolant channels. And but tritium and iodine-131 is expected in case of failures only. We don't expect iodine-131 normally. Some xenon can come. And so basically tritium has to be controlled. So I would like to mention here that NPC has done very wonderfully in gradually controlling the tritium discharges. And I think MAPS initially there were the quantities of tritium leakages were more, and gradually as the years went by, the tritium discharges were brought down, and they have been brought down to very low levels now. And being a part of VANO, they could bring the plants to world standards, I would say. So that way our power plants are of world standards, and we have hardly any discharge from the power plants. Now, spent fuel reprocessing, mainly what can come out is krypton 85 during the dissolution, and a little bit of iodine 129, which is not measurable so far. We have been trying to measure, and cesium 137, ruthenium 106, these are mentioned, but these are also not measurable in the off-gas streams. See, actually there is a off-gas, very good off-gas handling system, and then the ventilation system with multiple off-gas filters, HEPA filters. So we have seen that, and testing the systems at various levels, we have found that no radioactivity in form of particulates go out, and so no cesium or ruthenium can escape. Then the WIP, vitrification of high level waste. Yes, vitrification, the off gas which comes out from the melter contains cesium and all the activity which can become airborne, and these are treated in a elaborate off gas system, and then virtually nothing goes out. Again, the stack samples are regularly checked, and no radioactivity is found in the stack samples. So though we write some names like cesium 137, ruthenium 106, these are not found actually. I think I have to make it faster now. So special air filters are used like HEPA filters. HEPA filters were developed in BARC, and now it is indigenously produced in India. Iodine filters are also used. They were also developed in BRC, and KI, KOH coated iodine filters are also provided for monitoring of iodine in FBTR stack, in other stacks. So CWF also provides these filters, the KI, KOH coated small iodine filters. And CWF is responsible for testing all the HEPA filter installations and anti-filter installations of Kalpakkam and Kudankulam. Coming to solid waste management, as I said, once the properly segregated waste is received at CWMF, there are several techniques employed for treatment of the solid waste. Compaction, incineration, and of course melt densification are the processes. Coming to compaction, the compressible waste, they are packed in drums and they are placed inside the compactor. This compactor was actually is already operating compactors. A compactor is available at BARC Bombay with Waste Management Division, and we have taken the design from there, and we got it fabricated again by a contractor. And the beauty of this compactor, which was designed, was that the two closing sides of the compactor, the sealing is very good. Once the door comes down after the placement of drum, no air will leak out of the compactor chamber. The sealing is so beautifully done by gaskets, four-side gaskets, and a vacuum system. So rest is like the BRC compactor, and it gives very good volume reduction. After the compactor has become operational at CWMF, the uh, total waste disposal has come down, has been reduced to half the original amounts. Say if some 900 meter cubes were being disposed every year, now only 400, 500 meter cubes are being disposed. So that is a very good achievement, I would say. Solid waste, the other next solid waste treatment which I will talk about is incinerator. This incineration also is an early introduction to CWMF. This has been operating for quite a lot of years, right from 2000 or even before that. Sorry, even after 84, it was operationalized. Though it initially had problems, but it could be used, and it has been under constant operation actually. And the HEPA filters, which are the main, the final off-gas system filters. See, it has got several systems, several components. The settling chamber, cyclone, bag house, and then the HEPA filters. These HEPA filters are regularly tested for its efficiency and working. So, and we get the highest VRF of among all the solid waste treatments in incineration. Of volume reduction factor is between 50 to 80. This melt densification system was developed at CWMF, and I can proudly say that this is only one in the world. I mean, this is the first in the world, this application of melting. It's a very simple thing, melting the plastic waste and reducing its volume. And Dr. S.V.S. Rao had initiated this the research on this, and we made this the first one, that is the batch type system, and later a semi-continuous system was designed and installed. You are seeing the semi-continuous system here, and some of the melted and volume reduced plastic pieces. So here the advantage is that the radioactivity gets well trapped in the plastic, and the volume also gets reduced. solid waste disposal is done. Yeah, here regarding this NSDF, I just wanted to say that we take care to see that no radioactivity is going to the ground environment also. The near surface disposal facilities are engineered facilities, and there are three types of facilities: brick wall trenches, RCC trenches, and tile holes. And depending on the activity, radioactivity present, we um, dispose them in the various facilities. As we go to the higher engineering, the number of barriers keep increasing from the brick wall trenches to RCC trenches to tile holes. CWF is also doing this spent radiation sources management, and after so this I will just skip now. This is one of the activities done at BRC and at CWF for the entire India. So I just wanted to mention regarding pressure tube management. Pressure tubes of MAPS reactors 1 and 2 were replaced in 2002 and 2005. And these campaigns were, it was a joint campaign between MAPS and CWMF. And in 2002, they were cut into two pieces and disposed in tile holes and occupied a good number of tile holes. The next campaign in MAPS 1 campaign, 2005, it was decided that we will not do this disposal directly. We made a pool, SS pool, and it was stored in, all the tubes were stored in an SS pool underwater, and the water quality was maintained. And after we got permission from the safety committees that for 5 years to 7 years we'll store it here, and then we will be able to, we'll plan in the meantime for a better management of the pressure tubes. And in 2012-13, we took up the pressure tubes again, chopped them into small pieces, and compacted and disposed in drums in tile holes, which occupied much less space. So here I would like to say three people: Sri Chennakeshavulu, Sri Anji Reddy, and Sri B. Madhu, health physicist. They were the pivotal people who actually managed the entire thing, and I am proud to have such colleagues here. Now I'll come to next slide. Hull management. Yeah. See, we have when we do reprocessing, the zircaloy hulls come out and they are sent to CWMF, where they are stored in SS drums. Now these hulls are temporarily stored in tile holes because we cannot dispose them as they are alpha waste. So we, from the beginning, I have been thinking that we should be able to decontaminate these hulls, and we should be able to make them non-alpha so that we can dispose them as a normal rad waste in the tile holes. And I am very happy to say that it has been achieved in lab scale. Our colleagues, Sri Shanmugamani and Anji Reddy, they have successfully decontaminated hulls, and now a engineering scale trial in hot cells are being planned. Today I was talking to Mr. Sunil, who is also involved in this planning actually, because it has to be done at WIP, and he is the man at WIP. So I will now go to the next slide. HLW and ILW treatment. This is now coming to, yeah, I think I have to skip now. We have less time, no? Sir, can I take some more time? Glass is the best matrix because of all its properties. It's established long-term integrity, highly chemically durable, high and then good thermal and radiation stability, high corrosion resistance. So glass has been selected for emulation of HLW. So here again, like I was talking about chemical treatment, the HLW treatment also is dependent on the waste composition. When we take the waste from a particular tank, we have to characterize the waste and see what are the components present in it. In fact, some of the components would actually become part of the glass. They are glass formers and modifiers. So we need to take that into account while deciding the uh, quantities of the glass fit to be added and what will be the final component of the glass. So now the vitrification, this slide shows the stages of high level waste management. The HLW from the concentrated tanks, they are coming to WIP. In WIP again, they are further, HLW is further concentrated actually. And then it is vitrified, it is converted to glass, and then the canisters are remotely welded and they are transferred to the interim storage at VWSF, where it is kept in air-cooled storage, and it would become eligible for sending to a deep geological repository after maybe 50 years. So this is a picture of the Joule-heated ceramic melter which is used in WIP. WIP Kalpakkam boasts the largest melter in India, and I am told by Sri Sunil that it is the third largest in the world also. This melter was commissioned in 2017 and is still operating. It has completed its, so to say, the life, and it has seen several 56 months of operation. So even that becomes a world record, a melter running continuously for 56 months, and it has produced some 77 canisters so far, of which of course 76 have been already sent to VWSF. So both the facilities are working excellent way. The melter cell is again specially designed. It has got place for two melters. One melter, once it becomes unusable, can be packed and kept in a shielded box, and the second melter can be installed and used. So the WIP also has treatment facility for intermediate level waste. Intermediate level waste is basically alkaline waste containing cesium and strontium mainly, and some alpha. So this, I think I will not go through the full flow sheet now because we don't have time. Basically, we are using resorcinol formaldehyde and IDA for removing the contaminants. And the category 4, even after this treatment, it is still category 4, and this has to go to CWF for further treatment. The resorcinol formaldehyde resin, once it has seen its life, is fixed in cement. And this is a flow sheet showing the cement fixation. Actually, it is transferred to a resin batching tank, and through this tank it is fed in a cell into the cement drum and fixed in cement, and from where it goes to NSDF for disposal. The VWSF, the vitrified waste storage facility, was commissioned recently, 2 years back, and it's an air-cooled facility for storing the with 4 vaults, and it can keep up to around 2000 standard size canisters and 600 die canisters among 52 numbers. So each canister holds HLW generated from 10 tons of spent fuel, that is 800 bundles. As you can see, here 4 canisters are going into one location, one thimble tube, and ventilation arrangement is there to cool it continuously through the stack in a naturally ventilated system. This is working very well. Successfully, 76 canisters have been transferred into this facility. Another view of the vitrified waste storage facility. Yeah, the uranium oxide plant, which is an extension of CARP and CARP2, this had become necessary because to cater to, when both the plants are operational, to cater to that, to take care of the ADU production, this plant was made. And during this, it produces ADU filtrate, which is 75 grams per liter ammonium nitrate. And this is very high compared to the limits, environmental discharge limits, which are in milligrams per liter. So a denitro system has been commissioned. This also is a recent introduction, again informed to me by Sunil. I am already retired and out of the plant. So the team there, Mr. Gain, Sunil, and all the engineers, the chemists, the entire team is working very well in WIP. And this system has been finally commissioned, which is it has got this subsystem of pre-concentration, then solid handling system, heating systems, and feed system, and off-gas system, of course. So now I wanted to just say regarding the future, actually the hello?
You carry on.
Yeah. Actually, as I was telling that the improvements are continuous, and the waste management people, they don't stop. They are not satisfied with just what is going on, and the plant is functional well, everything is working nicely, fine. But of course, we are looking forward to zero discharge, which is an ambitious plan, which is not easy at all, and which is a challenge. So this is the proposal now. After the removal of uranium and plutonium, cesium is removed, is separated, and then actinide and lanthanides are separated. Again, from lanthanide, using this DEDCA and CABTP, lanthanide rare earths are separated. So see, once we separate out the actinides from the lanthanides are of lower activity and lower half-life. So they can be, then quantities are also much less. So now the actinides go for antimony separation using hydrous zircon, and lanthanide, and then it goes for annexation treatment, so that finally we end up with LLW. So this is a plan that we are able to reduce the volume of high level waste to very low volumes, and so that the load on the future generation is minimized. So waste generated per ton of spent fuel reprocessing in direct vitrification is 50 kg, and after this partitioning it will be 15 kg. So it is coming down to less than 1/3, and it's very good, I would say. and a little bit about the integrated nuclear recycle plant. Kalpakkam's INRP, integrated nuclear recycle plant, is the first one to be integrated. It was our Dr. Shekhar Basu's dream that we will integrate the plants, and only then the plants can function in an optimal manner. And after his dream has been really fulfilled by Shri Ravi, our CE, who has uh, finally brought the plants together, the management of the plants. And when I say the management has come, the physically the plants cannot be brought together because they're already constructed. What has happened is the operation is a single group, the maintenance is a single group, and that way the there is a and the entire thing is under a common plant superintendent. So what happens is the like a GM, common GM. So Shri Gain is looking after as GM of the plants, and the entire uh, team is working together in a much better way. Now the reprocessing plant cannot tell that I have made waste, you take it. Or waste managers cannot blame reprocessing plant for pointing fingers at them that you have not given me the right type of waste. You are making my life difficult. We have to sit together and solve the problem, and this is really happening. And I'm very happy to say that this has been possible. And again, I would like to thank all my seniors and my predecessors. I like to thank Sri Gain, Sri Ravi Sab for the excellent support and cooperation and what I have got from them. So thank you so much. And thanks to the audience for patient listening. Thank you.
Yeah. Thank you, Shri Paul. You can take some questions.
Yeah,
Yeah.
I'll hold it. Yeah. Thank you, Mr.
Yes,
Paul.
please.
Very nice journey through the whole process of waste management, all the processes you have told. And that too, the commendable part was with you have given the due credit to all the key people. And
Yeah.
that was really great about you. This topic is very important because whenever we go to public, I have been going to public during Jaitapur. And just a moment, sir, I will come to you for a question.
Sure,
Dr.
sure.
Rastogi, I will come to you. Yeah. So whenever we used to go to public, the public have two problems. They are sentimental about two things. One is that accidents like Chernobyl, Fukushima, and TMI. And the second sentimental point is you are going to have 50,000 years of radioactivity for our unaccountable generations, and then you are going to destroy them and all those things. So this gives a very good light on how we manage the radioactivity and waste processing and how we always keep in mind the load on the generations. Actually, I would suggest INS to convert this absolutely technical presentation, which is good for us, to a popular presentation, which can be given to public, and we can convince the public that, well, what you think about the waste management in nuclear plants is not really that detrimental as you think. So this is that way. It was a fantastic lecture, and really thank you very much. I think now we can go for question and answer sessions because there are a lot many questions and a lot many people interested. So first question was asked by Mr. Vaidya, PR Vaidya. Are you there, Mr. Vaidya? Can you please ask your question? Okay, I will read out the question. Has India identified sites for deep geological repositories? Can you answer, Dr. Paul?
This is still under review actually, and I am not the person to comment on this. I am already retired, and yeah. So,
okay. The next question was from Lalita. Can you please ask the question if you are around, Lalita, please? Her question is that what is the criteria to send the vitrified waste after the interim storage to repositories? How do you decide that when it should go?
Yeah, this is, see, basically the waste when it is vitrified is very hot, and it actually it has to decay the a few half-lives of say at least one half-life we are seeing of the cesium strontium, and some other radioisotopes which are present which are of shorter half-lives, they will decay, and the self-heating and the core temperature, that it should not de-vitrify the core of the glass, that should not de-vitrify by any chance. So we have to wait till then, till it can be sent to a place where it will not get the natural the force cooling, air cooling which we are providing at VWSF.
Yes.
So that becomes the criteria.
Okay, thank you very much. Dr. Rastogi, you were interested in asking a question. Can you please proceed?
First of all, I will congratulate Mr. Paul for dealing the entire waste management system from low level to high level waste. And
Thank you, sir. Thank you, sir.
my in between some questions have been asked. Can I comment on that? With respect
Yes, sir,
to
please.
with respect to disposal in deep geological foundation formation, as I know that it has been deferred long back. I don't know why, because that is one of the reasons that how to take care of high level waste even after storage, maybe about 30 years or 40 years in your interim storage facility. Finally, it has to find a place in some deep geological formation because it needs several thousands of years of isolation from the nature. So this is my comment with respect to deep geological formation disposal. Now, uh, I am very happy to learn from Mr. Paul that their interim storage facility has been operational since 2017, and it has a facility up to 2,000 canisters, and about 65 or 70 canisters have already been placed there. So it takes care of the decay heat, which is very much there in the beginning of the high level waste. So the decay heat has to be removed, and then only the question comes its final disposal. In this connection, I just wanted to add that the geological group in BARC under one Mr. R.K. Mathur, they did a in Kolar Gold Mine at minus 700 feet deep, uh, simulated simulated decay heat from electrical system and different orientation for several years, and it was finalized that what how much distance has to be made between the two canisters, and that became the basis of interim storage facility which has been functioning in Tarapur and which is now functioning in Kalpakkam, and I believe that it is following the same engineering detail as has been in Tarapur. So this again I am very happy to give my impression that the waste management system as it is now is taking care up to interim storage facility for high level waste. So for the low and intermediate level waste, it has been there for the last almost 4 decades or so, functioning at various nuclear power plants and it has been functioning very well. So once again I congratulate Mr. Paul for his presentation right from the scratch to up to high level based management. Thank you.
Thank you, Rastogi for your comments. I see hand raised by Dr. Amar Garg. You can ask the question, sir.
Sir, am I audible?
Yes, sir.
Yeah.
This lecture is unique combination of chemistry and engineering. And I feel that this lecture should be presented to some university chemistry graduates, whether they could realize that how the simple precipitation process, say for cyanides, the useful radionuclide like cesium-137 that can be precipitated and other things. I've really enjoyed this lecture very much, and I appreciate the presentation, excellent presentation by Dr. Biplob. Thank you very much, Indian Nuclear Society, for arranging this lecture.
Thank you, Dr. Garg.
Thank you, sir.
There is one question from Mr. Tiwari. Can you ask the question, Tiwari ji, please?
Good evening, sir. Am I audible?
Yeah, you are audible.
Yeah.
Please go ahead.
Sir, I'm from the nuclear fuel complex. I have seen that the zircaloy waste is there, which you are going to manage that. What we should do so that this zircaloy waste can be reutilized for fuel production?
Yeah, this has been there in my mind from the beginning, actually, that so much of zircaloy waste we are accumulating, and now if the hulls we are able to decontaminate, we'll have still larger quantity of zircaloy, and we should utilize it. And once when I went to NFC, I talked to my batchmate Meena Ravindran, and she was telling that there are some difficulties, like the way they handle. I remember the reactors, it's open from top, and the gases come out where they really dissolve the zircaloy. I was seeing the plant which uses scrap, which recycles the zircaloy scrap. So it dissolves. Actually, it is using a gas, no?
Yes, chlorine.
Yeah. So this it's an open reactor kind of something comes out. I remember that it's not totally enclosed. So we can actually, if NFC and NRB work together, and NRG also, if we work together, we can definitely try to utilize this zircaloy, plan for the recycling of zircaloy into fuel fabrication. Because anyway, FRFCF, as I understand, is planning to do fuel fabrication with fuel material which are radioactive and having some amount of dose. I don't know the exact level of dose, but if the fuel fabrication facilities are gradually gearing up to take up radioactive the dose containing fuels, then probably the hulls also could be reutilized to use the zircaloy.
Thank you.
Thank you. Thank you, sir. Dr. B.M. Mishra, please.
Thank
go
you.
ahead.
Excellent presentation, Mr. Biplob. I just was interested to know how much cesium and strontium recovered from these facilities are used in the industrial applications, as you mentioned.
In cesium pencil, you're talking of cesium pencils?
Yeah. Cesium
Yeah,
and
actually,
strontium are recovered and used for the other industrial applications.
okay, this is being done at BARC, so the quantities I will not be able to tell. But only one thing I know is that the quantities of cesium-137 which we have is huge. And right now there is no demand or market for that much quantity of cesium.
Mr. Vikay Bhargav, please mute yourself, Mr. Bhargav.
Okay, thanks.
Yeah, I was, yeah. that I wanted to say that as of now, we don't have applications to utilize the huge quantity of cesium which we have. But tomorrow, gradually, we may have. Because irradiation is a method by which we can irradiation, if it is acceptable to the agricultural users.
Right.
Maybe more irradiation facilities will be using the cesium.
Thank you, sir. Thank you.
Dr. Manchanda, you can please proceed ahead.
This Shri Biplob, this cesium, I understand it is being regularly supplied for blood irradiation. And that demand is, quite a bit. So please check up about this part. In fact, in a recent exhibition of DAE, this blood irrigator, they had put there that cesium pencils are being supplied for blood irradiation.
Yes.
Okay.
It has been.
Now,
It has
yeah,
found an
I mean,
application.
this is being done actually.
Yes,
But I have a small question actually. This is, when I was in surveys, Mr. Natarajan from the reprocessing group of IGCAR, he had, I had heard him and we were discussing many times the integrated facility for the fast reactor fuel actually. So, so I guess there must be the waste management also must be a part of that integrated facility.
Definitely.
So can you throw some light on that if you have some idea?
See, it's as I was telling, FRFCF, that is fast reactor fuel recycling facility, is coming up in a very big site opposite to the PFBR site. And so the plan is that it will, the solid in, solid out, that is the solid spent fuel will be coming from the PFBR into this facility. It will be reprocessed. And the fuel will be maybe with some interim storages because the activity level will be quite high initially. So then it will go back to fuel fabrication. This facility has reprocessing, waste management, and fuel fabrication, all three together.
Okay.
And all the necessary utilities with that. It's a huge plant and well planned, and it is being done. So right now.
Yeah. What is the status now? What is the status?
It is under construction. It is under construction. I will not be able to tell you the exact status. Some of the facilities are nearing completion, like waste management. Part of waste management, as I know, is getting ready. Part of waste management. I don't know about the other parts. Fuel fabrication, reprocessing. Reprocessing particularly, really, that was that had some hiccups, I think. So I don't know really what is the status right now.
Anyway, okay, thank you.
Yeah. Any other questions in the audience?
Maithili has a comment.
Yeah. Maithili, please.
Maithili is asking, can you please comment on metallic waste forms for high level waste? I don't know what that means. Maithili, if you are there, can you ask your question? She's not there.
Yeah.
High level waste in metallic waste forms.
The question is, can you please comment on metallic waste forms for high level waste? What are the metallic waste forms for high level waste?
No, actually, I am not aware that well about this. As far as I know, I have been seeing more of ceramic forms like syn rock and various types of glass or synthetic minerals. But pure metallic waste form I have not come across. There may be some new studies coming up, but I have not come across.
Okay.
I think if there are no more questions, I will hand over the things to Mr. Swapnesh Malhotra for.
Yes, sir.
Yeah. Mr. Malhotra.
Thank you very much. Am I audible?
Yeah.
Sure.
Yes, sir.
Yeah. So first of all, let me congratulate and compliment Mr. Biplob Paul. I don't know whether he recalls knowing me. We have interacted when I was at DAE. So a fantastic lecture. Please accept my compliments. It was, in fact, at times I felt that Mr. Paul has taken us back to our training school days. It was so in such a subtle language, in a subtle manner, he has told about the complete waste management policy and technology. So once again, accept my compliments. I also express, as Secretary INS, I express my gratitude to the Executive Committee of INS, particularly our respected President, Shri S.K. Mehta, for guiding us for this very important and now well-established webinar program. We, as you know, already 28th webinar has been delivered. And particularly, I would like to offer my compliments to the webinar subcommittee, very ably led by Dr. Ramarao, and Mr. Dharne is there, others are there. So my compliments to the entire team. And then I would like to thank our audiences. Today I was very happy, particularly that I think after a long time we had sizable audiences. Some of them have left at present. It has again come down. So I thank all the INS members and all the audience who were very patiently listening to our webinars. And I also thank Shri G.D. Mittal, who is presently the acting secretary, myself being away from the country, for particularly propagating the message about these seminars, these webinars, and putting them on our INS YouTube channel so that people can follow these lectures or these webinars permanently. If they have missed, later on they can follow it. I also thank once again all the audience. And here, in fact, normally we tell about our forthcoming webinar, but today, I think so far I have no information about the next webinar. So whenever we are ready with that information, you will come to know about our 29th and subsequent webinars. Now, before I close up, I have certain observations as Secretary INS. I request, with folded hands, I request the audiences that kindly maintain the decorum during the webinar. There are disturbances in terms of visuals as well as audio forms. There are people talking to family members or talking on phone. I think a general culture we can develop that when the speaker has started speaking, we have no business to keep our mic on. And in fact, it is not required to keep our camera also on. I always do that. So with folded hands, I request all the esteemed audiences to kindly follow this practice. And I will not like to make any individual comments about anybody, but I think display of motherly love and display of maybe other sentiments, they can be reserved for our private times, but not during the webinar, particularly of INS. With that, I thank everyone once again, and bye-bye. See you in the next webinar. Thank you very much.
Thank you, Bharat Vijay. Thank you very much. Thank you, Shri Paul. See you again. Join us in the next webinar, which will be on the 17th perhaps. So we'll notify that also. So thank you all viewers. I had a nice time. I am now closing the recording.